Hey everyone, welcome back to The Explainer. So today we are going to unpack what is honestly a classic and, yeah, pretty math-heavy electrical engineering problem. Now, I know it might look a little daunting at first glance, but don't worry. We're going to decode the logic behind all these equations completely step by step. Take a look at our source material for today. It's this dense, handwritten page just absolutely packed with complex numbers and circuit diagrams. This is exactly the kind of thing you'd see staring back at you on a high-level exam, right? Well, we are going to take this chaotic-looking page and transform it into a super manageable logical sequence. Seriously, by the time we finish up here, you're going to understand every single pen stroke on this paper. So, here is our game plan. 1, we'll extract the problem in parameters. 2, we'll convert the star connection to a delta connection. 3, we'll calculate the line current. And 4, we'll wrap it all up with a final results summary. All right, let's jump straight into section 1, the problem and parameters. Let's pull out our clues. Okay, we've cleared away all that visual clutter. Here are our starting tools. We're given a balanced star-connected load, and its phase impedance, which we write as Z sub Y, is this complex number, 8 plus J6 ohms. We've also got a line voltage, or V sub L, of 415 volts, and finally, a frequency of 50 hertz. So what's our actual mission here? We need to convert this into an equivalent delta connection and figure out both the delta impedance per phase and the line current. We've got our clues, so let's get to work. Moving right along to section 2, converting star to delta. Time to do some translating. Now, because our source explicitly tells us this is a balanced system, we have this absolute golden rule we can rely on, and that rule is the equivalent delta impedance is exactly equal to 3 times the star impedance. Literally just multiply it by 3. This one simple formula is the master key that unlocks the whole mathematical conversion for us. Let's actually apply that golden rule. We take our multiplier of 3 and we distribute it right across our complex star impedance of 8 plus J6. So 3 times 8 gives us a real component of 24. And 3 times J6 gives us an imaginary component of J18. And boom, just like that, we've got our delta impedance in rectangular form, 24 plus J18 ohms. But as you know, in engineering, we almost always need this in polar form, meaning we need a magnitude and an angle, just to make all our future calculations way easier. So, to find that magnitude, we're basically just leaning on the Pythagorean theorem. We take the square root of 24 squared plus 18 squared, which gives us the square root of 576 plus 324, which is the square root of 900. And the square root of 900 gives us a beautifully clean 30 ohms. That right there is a huge win. We've officially found the magnitude of our delta impedance. But remember, impedance in AC circuits has a directional component, right? We need that angle, theta. To find it, we just take the inverse tangent, or arctangent, of our imaginary component divided by our real component. So that's 18 divided by 24, which reduces down perfectly to 0.75. If you pop the inverse tangent of 0.75 into your calculator, you're going to get exactly 36.87 degrees. All right, with the magnitude and the angle locked in, our first major objective is totally complete. Our final delta impedance is 24 plus J18 ohms, which is perfectly equivalent to 30 ohms at an angle of 36.87 degrees. Look at that, half the problem is officially solved. Which brings us to section 3, calculating the line current. Let's shift our focus to how the electricity is actually flowing. You know, whenever you're staring down a multi-step calculation, it always helps to build a little micro roadmap so you don't get lost in the weeds. Here's our quick plan for finding the line current. Step 1, identify the phase voltage. Step 2, calculate the phase current. And step 3, calculate the actual line current. It's just a nice, simple, logical chain reaction. So step 1, a really fundamental rule of circuit topology kicks in right here. In a delta connection, the phase voltage is exactly the same as the line voltage. Since our original problem stated the line voltage was 415 volts, well, our phase voltage is also 415 volts. How great is that? Absolutely no math required for this step. Now, with our phase voltage in hand, calculating the phase current is incredibly straightforward. Honestly, it's essentially just Ohm's law for AC circuits. We take our voltage, which is 415 volts, and we divide it by the magnitude of our impedance, which we conveniently figured out was 30 ohms just a minute ago. So 415 divided by 30 gives us a phase current of 13.83 amps. I love it when the steps just cascade perfectly into one another like this. Okay, we've made it to the final calculation step. To find the line current in a delta setup, all we have to do is multiply our phase current by the square root of 3. So, setting up that equation, it's the square root of 3 multiplied by our 13.83 amps. And running those numbers brings us to our line current, 23.96 amperes. We have successfully wrangled the current and found our absolute last missing variable. We did it! Finally, Section 4, the final results summary. Let's bring it all home. Here they are, the 2 final answers we just successfully unlocked by sticking to our procedural, step-by-step approach. First up, we found the equivalent delta impedance per phase to be 30 ohms at an angle of 36.87 degrees. Second, we determined the line current to be exactly 23.96 amperes, which, as the original source points out, comfortably rounds up to about 24 amps. Let's just take a quick look back at the bottom of our original source document. Check out those final red underlines. We started at the very top of this dense, confusing page, and by applying clear, structured logic, we've mastered every single step all the way down to this final confirmation. Seriously, you now deeply understand exactly how every single one of those numbers was derived. And that actually brings me to a final thought for you to ponder today. We took something that looked incredibly complex and honestly made it pretty easy, simply by breaking it down into manageable, sequential steps. So I have to ask you, what other dense, intimidating engineering problems are sitting on your desk right now that you could absolutely conquer using this exact same structured method? The answer? Literally all of them. Keep focusing, keep breaking things down, and keep learning. Thanks so much for joining me on this explainer, and I'll catch you on the next one.